All right, so good morning. We will start. Another students are there. So we will start. So last time we had a couple of classes. Both of them are just like introduction and refreshing classes. And you were shared with the syllabus and detailed textbook details and everything already. So now we can start going straight into the lectures. Right, so I'll start with chapter 1. Chapter 1, right? So it is basically the numbers and the real number system, right? So as Professor Srisat Kunraja says, it is about realizing the infinity, right, at the beginning. So we'll start with right, so we will start with the real number system, right? So first of all, let me show you the notation. You have already known about numbers, right? So we call right, so we will talk about set of real numbers here, right? So right, R with an extra line in front, right? That is how we will denote the real number system, right? So whenever I write R like this, right? So we call it math R, right? So whenever we write R like this, we call this as the real number, real set of real numbers, right? So set of real numbers means all possible numbers you know, right? All kinds of numbers you know is called set of real numbers, right? So you basically know certain numbers, right? So let me tell you numbers like this. So first of all, you know 1, 2, 3, like that, right? So these are some of the first set of numbers you heard in your life, right? So we call it natural numbers. And so we denote this by n, right? And then you have 1, 2, 3, and then you put 0, and then you have minus 1, 2, 3. So basically, right? So next, you heard about these kind of numbers, right? Once you get to know about minus, then you know, okay, there is 0, minus 1, minus 2 are also there, right? Not just 1, 2, 3. So these are called integers. Right? So we denote it by a capital Z, right? So all those number system sets, right? With those letters, we put an extra line, right? So we put extra line, right? Right, Z with the dash extra is called integers. N with the extra dash is called natural numbers. Right? So once you know these numbers, then you know you can divide, right? 1/2, 5 upon 3, sorry, 3 upon 5, like that, right? So 1 upon 2, 3 upon 5, blah, 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 and minus 3 upon 4, and like that, right? So you have heard about these numbers, right? Fractions kind of things, right? But within that, these numbers will also come, right? So 1, right? So 1 will come here, and minus 1 will come here, and all those numbers will come here, right? So somewhere here 0 will come. Like that, these numbers will also come within the fraction, right? Because 1 is 1 upon 1, right? 0 is 0 upon 1, right? Minus 2 is minus 2 upon 1, right? So those numbers also you can write them as fractions. So altogether, these numbers are coming as fractions, right? So you learn about those numbers, right? Fractions. So we call it rationals. Right? So we call as Q, right? Rational numbers. So any number which can be written as a fraction, right? So if you have a number that can be written as a fraction, that is called rational number. So you have Q. Right? And then after studying about rational numbers, then you started learning about square roots, right? You learn about square root of 2, square root of 3, square root of 5, like that. Those kind of numbers you learn, right? So, right, square root of 2, square root of 3, minus square root of 2, etc., etc., etc. Right? These kind of numbers also you heard about these numbers, right? So that means the numbers which cannot be written as fractions, right? The numbers which are not rationals. There are numbers exist that are not rationals, right? So that those numbers we call it irrationals. Right? So these numbers are not rationals, right? So we call it irrationals. So for that, we use the standard set theoretical notation Q complement, right? So you learn set theory, basic set theory in the O levels, right? So a set and then everything else which is not in the set is called a complement of the set. So we call irrationals, right? That is Q complement, right? So this is how, right, the sets, the numbers looks like, right? So basically you can see, you can think of this, right? So the real number is the big set. Within that, you will have Q, right? Rationals as a set within that, and everything within R but not in Q are called Q complement, right? So you know that. So rationals are inside the reals, right? Within the rationals, you have integers. Right? You have integers, and within the integers, you will have natural numbers. Right? And so this is how number sets looks like, right? Integers are the smallest set you know, and then natural numbers are the smallest, and then you include them within the integers, and then integers goes inside the rationals, and then there are irrationals, and all of them goes inside the real numbers, right? So later on, you learn in A-level, you learn complex numbers. And so I just mentioned here, these are complex numbers. And complex numbers is a larger set than the reals, but here in this course, because this is about real analysis, not imaginary analysis, so this is real analysis, we will stop with the real number system and everything inside the real number system. We will not go into complex numbers here, right? But we will focus on real number system, right? So these are the notations you are going to face in this course quite often, right? R, right? Not just in this course, everywhere in the university mathematics, you will see these notations. Right? R means real numbers, N means natural numbers, Z means integers, Q means rationals, and Q complement means irrationals, right? There are certain other types of numbers as well, but whenever the time comes, we will talk about that, but not here. So basically, this is how the number systems are there, right? So we will turn our focus into real number system, right? As I told you in the first class, right? So we have to develop things from the scratch, right? So the basic idea is about realizing all the real numbers. So we will start with the basic operations that exist in the real numbers, that is addition and multiplication, right? So addition and multiplication together with 0 and 1 basically build up the real number system, right? So we will talk about that first in the name of axioms. Okay, so the first step, first thing we learn here is called the algebraic properties of real number system, all right, or the set of real numbers. So we will talk about on the real number set. Right, so we will focus on two operations in the real number set. One is called addition, right? We use a plus notation for that, and dot is a multiplication, right? So we call it multiplication, right? So here, the properties, I'm going to list down a few properties here, right? And these properties, we are going to believe them without any proof, right? So right, so these are called axioms. These properties are called axioms, right? Why we give the name axiom? Because we are going to believe that these properties are true without having any proof of that, right? So we don't, in mathematics, we don't believe things without a proof, right? So we can prove everything by using mathematical constructions, but you always have to have certain facts at the beginning to prove them, right? So this is one of them, right? These concepts are one of the things which we are going to take as true without having a proof of that. We call those kind of facts as axioms, right? So in this course, we will develop or we will see a few axioms, right? So this is the first set of axioms which are known as algebraic properties, right? So let me list them out. The first one, so let me name A1. That means it is the first property associated with the addition, right? A stands for addition, 1 stands for the first property, right? A1. Right? So A plus B is equal to B plus A in real numbers, right? So except infinity, right? So Professor Srisat Kundaya also explained about this in the last class. This may not be true in infinity case, right? But as long as you know the numbers, right? If you know A and B as any real number, right? Whatever the number you know, adding A with B and B with A are same, right? Within the numbers you know, right? So as of now, you don't know infinity yet, right? So you only know the finite numbers. So whatever the numbers are, you have A and B. A plus B is equal to B plus A, right? For any real number A plus B, right? This notation, right? So this notation this is read as for all, right? V and a cross or something like a upside down capital A, right? So this means for all, right? So that English itself is enough to explain what do we mean by that, right? For all or for any A plus A comma B in real numbers. So for all real numbers, adding and changing the order in adding does not matter. Right? So that's the first axiom. Second one, and this notation you know, right? And so this is set notation you studied in O levels, right? Right? For belongs to, right? So when we speak, we say in, but it actually means belongs to, right? So A comma B belongs to the set R, right? So axiom 2 is when you add 3 numbers, right? Again, you can add in any order, right? So you add the first 2 numbers and then the third number together, right? Or you can add the last 2 numbers together and then add the first number, right? So it doesn't matter in whichever order you are adding. Right? So this is called second property, right? So here A1 is also known as right. So A1 is also known as commutative property, right? So you can commute the addition, and A2 is also known as associative property. So there is associative property in the addition aspect. So this is A1 and A2. Now let us talk about A3 and A4. right? So the third property, A3, there is a 0 in the real numbers, right? Such that when you add any number with 0, you get the same number, right? So this is also an axiom or property in real numbers with addition, right? Which we are going to assume, right? So when there is a 0 in the real number system, such that whatever the number you add with 0 in whatever the order, you get the number again, right? So this is called existence of 0. Right. So first, the notation, this means the reverse E kind of notation is called there exists, right? There is or there exists a 0. And A3, this property is known as existence of 0. So let me write 0. Right, so this property is called the existence of a 0 element. Right. So once you get that property, right, existence of 0, then you get the existence of additive inverse, right? Okay, so once you know there is a 0, then you should be able to get a 0 from a number, right? So that says for any real number, there will be a minus of it, right? That is called additive inverse, right? So if you say 5, then there is a minus 5 there, right? So then when you add 5 with minus 5, you get 0. Right? Similarly, if you have a minus 3, you will have a plus 3. Right? Minus of minus 3 is plus 3, you know that. So for any number, there will be an inverse, additive inverse. Right? So this property is called, right? So again, notation, S dot D T is a short form of such that, right? Right, so whenever I write S dot T right here, that means such that, right? So this such that, instead of writing such that, again I will use S dot T. Right? So this is called A4 is called right, so this is called existence of additive inverse or existence of negative element, right? So some books use additive inverse, some books use negative element, right? So these are the 4 properties associated with the addition, right? Addition, the order does not matter, so it is commutative. So you can add any numbers at any number with anything and then add any other number, right? So that's called associative property. And then the existence of a 0 element and existence of a negative element, right? So these are the 4 properties associated with the addition. Similar type of properties we can develop with the multiplication as well. Right? So that I'm going to use M. Right? So now I am not going to rewrite the notations again and again, right? Because now you know the notations. So I will straight away write down the properties. M1, order of multiplication, it does not matter. Right, so A dot B and B dot A are same for all real numbers A comma B, right? So this is again called commutative property, right? This is called commutative in multiplication. Similarly, M2 is A dot B multiplied with C is same as A dot B dot C for all A comma B comma C in real numbers. Right? This is associative in multiplication. Right. M3, right? In addition, you get 0, right? That means 0 means whatever you add with 0, you get the same value, right? Similarly, in multiplication, whatever you multiply with 1, you get the same value, right? So, okay, so existence of 1 or existence of unit element, right? So some people call unit element because whatever you multiply with the unit element, you get the same value, right? So 5.1 is 1, 1.5 is 1, 1 dot minus 5 is 5, minus 5, and minus 5.1 is minus 5. So you know that. And similarly, inverse element, right? Existence of multiplicative inverse. Okay, so when you have multiplication, right, you know that if there is an A, then there should be 1 upon A, such that whenever you multiply A with 1 upon A, you get 1. Right? So when you have 2, you have 1 upon 2 and 2 times 1 upon 2 is 1. When you have minus 3, you have 1 upon minus 3, and when you multiply both of them, you get 1. Right? So that is also the fourth axiom in multiplication. So that means it is multiplicative inverse. So actually it is called reciprocal, right? 1 upon that number. So that is called reciprocal. So here one more thing is important, right? That number should be non-zero, because you know that 1 upon 0 is not defined, right? So in A levels or O levels, you study, right? Already learned that 1 upon 0 is not defined. There is no number called 1 upon 0, right? So you cannot divide any number by 0, right? So that's why 1 upon 0 does not exist. So that is why to have a reciprocal, you should have the number non-zero, right? So this multiplication property does not, the reciprocal property does not exist for 1, sorry, minus 0, right? So you have to have a non-zero number. Okay, so these are the properties associated with multiplication, right? So there are 4 with the addition, there are 4 with the multiplication. Now you can do both of them together, right? So you can add and multiply together, right? So for example, you can add 2 with 3 and then multiply by 1 upon 2, right? Or you can multiply 1 upon 2 with 5 and then you add 6, right? So like that you can do, right? So you can do both operations together at the same time. So we will see what kind of axiom is there for that, right? So that is called distributive property. So let me name this as D1, right? Okay, so you can add 2 numbers and then multiply with them, multiply a number with that, or it is same as multiplying the numbers separately and then add them, right? So that is what I told you. 2 times 5 plus 6, all right? So 2 times 5 plus 6 is same as 2 times 5 plus 2 times 6, right? Or you add 2 numbers and multiply them together. After that, the same as you multiply and add them, right? So this is called distributive property, right? So that means you can distribute the multiplication inside the addition, right? Or you can distribute the multiplication from behind inside the addition, right? Front and behind, you can do, right? So this is called distributive property, right? So these are the 9 properties. So basically there are 10 because there are 2 here in the distributive property, right? So there are 10 properties in the real number system, right? Associated with the operations, addition and multiplication, right? So these 10 properties are called algebraic properties of real number, right? Or algebraic axioms on real number, right? So by using all these 10 axioms, right? So all these 10 properties, we can prove any other detail we have in real numbers, right? So these are the only 10 in addition and multiplication, which we are going to assume that there is no proof for that, or we will take these 10 without a proof. All the other things, right, we can prove by using all these 10 properties, right? So I'm going to show you some exercises and examples where we will develop some results by using whatever the property we have learned here. Okay? So the first thing is uniqueness of zeros and ones. Right, so let's group these as exercises. Right, so we are trying to show that the additive identity, so we already know there is an additive identity, right? So there is a zero there, we all know that, right? So what we are trying to show here is, we are trying to show that the additive identity 0 is unique, right? Right, so let me write down the question. Show that additive identity is unique. That means there is no two different additive identity. There is only one additive identity, right? So one way of proving this kind of results, right, is by using that, assuming there are two and then showing them both of them are equal, right? So let me write the proof clearly here, right? Right, so they say that they want you to show that there is exactly one additive identity, right? So now let me see that whether if there are two, right? So I am assuming that there are two additive identities. One of them I name them as 0, 1, and one of them as 0, 2, right? So you know that so now because 0, 2 is an additive identity, right? Whatever the number you add with 0, 2 will give you the same number, right? So whatever the number you add with 0, 2 will give you the same number. So if you add 0, 1 with 0, 2, you will get 0, 1, right? Because 0, 2 is an additive identity. Similarly, but we assume that 0, 1 is also an additive identity. So whatever the number you add with 0, 1 will give you the same number. So whenever you add 0, 2 with 0, 1, you will get 0, 2, right? Whenever you get 0, 1 with 0, 2, you get 0, 2 because 0, 1 is an additive identity. Similarly, earlier we see that 0, 2 is an additive identity. So 0, 1 plus 0, 2 is 0, 1. So here you can see that the left hand side is same. And so this and this are same. So this is equal to 0, 1. This is equal to 0, 2. So when you combine both of them, you can clearly see, right? Same value is equal to 1 time. Once it is equal to 0, 1. The other time it is equal to 0, 2. So it means 0, 1 and 0, 2 are equal to 0, 1 and 0, 2 are same. Okay. So that is how you show that additive identity is unique. Right? Similarly, you can show that multiplicative identity is also unique. So I will leave it as a homework for you to work. And so let me know, write that as exercise as a homework. Right, so first homework is you have to show that the multiplicative identity is unique. Right? So let me write down 3 more homeworks just for you to think about, but I will do that in the next class. Right? So exercise 1. Okay, so these 3 are homeworks. I will do at least 1 or 2 of them in the next class, right? But you just try to think of how to do this, right? So imagine now you have only 10 axioms in your hand, right? The additive axioms, multiplicative axioms, and then distributive axioms. So try to see whether you can show this result. If Z plus A is equal to A, then you can understand that Z should be 0, right? That looks very clear. But the problem here is you have only 10 axioms in your hand. You know nothing else, right? So you have to use those axioms and then these 2 exercises, right? The additive identity is unique and multiplicative identity is also unique. Those are also now you know those results. So by using those 2 results and the 10 axioms, you try to see whether you will be able to show these results by using the 10 axioms, right? So these I leave as a homework, and I will talk to you in the next class tomorrow at 1. And on that class, I will try to do at least first 2 of these exercises, right? So I will stop here and then I'll see you on Tuesday at 1.